Welcome to Infinite Science. Today we're going to talk about something extraordinary, something that's fundamentally changing how we see the universe itself. Look up at the night sky. Those pinpricks of light scattered across the darkness like diamonds on black velvet have captivated humanity for millennia. We've gazed upward with wonder, asking the same questions generation after generation. Where did we come from? Are we alone? What lies beyond the edge of everything we know? For most of human history, these questions remained firmly in the realm of philosophy and mythology. But in recent decades, we've developed tools that allow us to do more than wonder. We can actually look back in time, peer into the birthplaces of stars, and examine worlds orbiting distant suns. And now, we have the most powerful such tool ever created. The James Webb Space Telescope is not just another observatory. It's a time machine, a cosmic detective, a window into realms that were, until recently, completely invisible to us. Since it began operations, Webb has been sending back images and data that have left scientists genuinely stunned, not just impressed, but fundamentally confused about what they're seeing. Galaxies that shouldn't exist, stars forming in ways we didn't predict, chemical signatures that challenge our understanding of planetary atmospheres, black holes that grew too fast, too early. The universe, as seen through Webb's eyes, is stranger and more complex than our best theories suggested. This is the story of what happens when you build an instrument so sensitive, so powerful, that it doesn't just answer questions. It reveals how much we still don't understand. This is the story of how the James Webb Space Telescope is rewriting the textbooks, one stunning discovery at a time. Let's begin. To understand why the James Webb Space Telescope represents such a monumental leap forward, we need to go back to 1990, when the Hubble Space Telescope was deployed into orbit. Hubble transformed our understanding of the cosmos. Its images became iconic, the pillars of creation, the deep field observations revealing thousands of galaxies in what appeared to be empty space. Detailed views of distant nebulae in colors that seemed almost too vivid to be real. For over 3 decades, Hubble has been our window to the universe, revealing wonders we never imagined, but Hubble had limitations. Its primary mirror, while revolutionary for its time, measures 2.4 meters across. It observes primarily in visible and ultraviolet light, the same wavelengths our eyes can see. This means that much of the universe remained hidden from Hubble's view, obscured by cosmic dust, or simply too distant for its instruments to detect clearly. As the 1990s progressed, astronomers began dreaming of a successor. They wanted something that could see farther, peer through cosmic dust clouds, and observe the very first galaxies that formed after the Big Bang. They wanted to understand how stars and planets form in detail that Hubble simply couldn't provide. They wanted to study the atmospheres of planets around other stars, searching for signs of habitability or even life itself. The concept that would become James Webb began taking shape in 1996. Originally called the Next Generation Space Telescope, it was later renamed in honor of James E. Webb, NASA's administrator during the Apollo era. But the technical challenges were staggering. To see the earliest galaxies, objects so distant that the universe's expansion has stretched their light from visible wavelengths into the infrared, the telescope would need to be optimized for infrared observation. This presented an immediate problem. Infrared is heat radiation, and any warm object emits it. To detect faint infrared signals from distant galaxies, Webb itself would need to be incredibly cold, operating at temperatures around -233 degrees Celsius. The solution was to position Webb not in Earth orbit, like Hubble, but at a location called the second Lagrange point, or L2, approximately 1.5 million kilometers from Earth. At this gravitational sweet spot, Webb could orbit the Sun while staying aligned with Earth, using a tennis court-sized sunshield to block the heat from the Sun, Earth, and Moon simultaneously. Then there was the matter of the mirror. To capture enough light from these ancient, distant objects, Webb would need a mirror far larger than Hubble's. The engineers settled on a primary mirror 6.5 meters in diameter, nearly 3 times wider than Hubble's, giving it about 7 times the light-collecting area. But here's the problem. No rocket fairing is large enough to accommodate a 6.5-meter mirror. The solution was ingenious and terrifying in equal measure. The mirror would be segmented into 18 hexagonal pieces, each coated in a microscopically thin layer of gold for optimal infrared reflection. These segments would fold up for launch, then unfold in space with microscopic precision. Each segment can be individually adjusted by tiny motors, allowing them to work together as a single, perfect mirror. The entire telescope would have to unfold in space like the most complex origami ever attempted. The sunshield alone required 139 release mechanisms, 70 hinge assemblies, 8 deployment motors, and approximately 400 pulleys and 90 cables. A single failure anywhere in this sequence could doom the entire mission. The original launch was planned for 2007 with a budget of $1 billion. As the technical challenges mounted, that timeline slipped. 2007 became 2011, then 2014, then 2018, then 2021. The budget swelled to nearly $10 billion. Critics called it a boondoggle. Some questioned whether it would ever launch, or if it did, whether this impossibly complex machine could actually work. The delays were frustrating but necessary. Each postponement came with good reason. Engineers discovering potential failure points, testing revealing weaknesses, simulations showing scenarios that needed to be addressed. This wasn't bureaucratic inefficiency. It was the painstaking work of ensuring that a one-shot mission to a location humans could never reach would actually succeed. Think about what was at stake. Once Webb launched, there would be no second chances. No repair missions like those that saved Hubble. No astronauts floating in space to fix a stuck solar panel or replace a faulty gyroscope. Webb would travel to a point in space farther than any human had ever ventured, and it would have to work perfectly on the first try. The pressure on the engineering teams was immense. They were designing a telescope that had to survive a rocket launch, unfold with perfect precision in the vacuum of space, cool down to operating temperature, align its mirrors to nanometer accuracy, and then operate flawlessly for years. All without any possibility of hands-on intervention if something went wrong. Finally, on Christmas Day 2021, Webb launched from French Guiana aboard an Ariane 5 rocket. The world watched with a mixture of hope and anxiety as humanity's most ambitious space observatory began its million-mile journey. What followed was 29 days of carefully choreographed deployment, the most nerve-wracking month in the history of space science. Each step had been planned, simulated, and tested thousands of times, but simulations aren't reality. Every deployment mechanism had to work perfectly in the harsh environment of space. First, the solar array deployed, providing power to the spacecraft. Then, over the following days, the sun shield began its careful unfurling. This was perhaps the most anxiety-inducing part of the entire deployment. The sun shield, 5 layers of material thinner than a human hair, each separated by a precise gap, had to separate and tension properly. If it tore, if it didn't fully deploy, if the layers didn't separate correctly, Webb's infrared instruments would be useless, blinded by the heat of view, the sun. But the sun shield deployed perfectly. Layer by layer, it unfolded and tensioned, creating the critical barrier between the hot side of the telescope, facing the sun, and the cold side, where the instruments would operate. Then came the mirror deployment. The secondary mirror swung into position on its support structure. The two primary mirror wings, each containing 3 of the 18 hexagonal segments, slowly, carefully rotated into place and locked. For the first time, Webb's primary mirror was fully deployed, a massive golden eye ready to observe the universe. But having the mirror deployed wasn't enough. Each of those 18 segments needed to be aligned with microscopic precision so they would work together as a single mirror. This process, called wavefront sensing and control, took weeks. Engineers commanded tiny motors to adjust each segment's position and curvature, slowly bringing all 18 into perfect alignment. Engineers and scientists around the world held their collective breath. Billions of dollars and decades of work hung in the balance. If anything went wrong, if a single motor failed, if a cable snagged, if a segment wouldn't align, there would be no fixing it. But against all odds, everything worked. By July 2022, 6 months after launch, Webb had completed its commissioning phase. The mirror segments were aligned to within nanometers. The instruments were calibrated and operating at optimal sensitivity. The telescope was ready to begin its mission. NASA released the first full-color images, and the world got its first glimpse of what Webb could do. President Biden revealed the first deep-field image in a special preview. Then, in a global media event, NASA unveiled a series of images that left even veteran astronomers speechless. And immediately, it became clear that this wasn't just an incremental improvement over Hubble. This was something entirely different, a telescope so sensitive and powerful that it could show us not just a clearer view of what we already knew, but reveal things we never imagined were there to see. The universe was about to become far stranger than we thought. When the first Webb images were released to the public in July 2022, social media exploded with reactions. Scientists found themselves openly weeping. Veteran astronomers, people who had spent their entire careers studying the cosmos, spoke of being overwhelmed by what they were seeing. The hashtag #UnfoldTheUniverse trended worldwide as millions of people saw the cosmos in a way they never had before. What made these images so profound wasn't just their beauty, though they were undeniably spectacular. It was what they represented, a fundamental expansion of what we can observe. Consider Webb's first deep field image, officially known as SMACS 0723. In a tiny patch of sky, an area roughly the size of a grain of sand held at arm's length, Webb revealed thousands of galaxies. But these weren't just any galaxies. These were objects, so distant that their light has been traveling toward us for over 13 billion years. We're seeing them as they appeared when the universe was only a few 100 million years old, in its cosmic infancy. To put that in perspective, if the history of the universe were compressed into a single year, with the Big Bang occurring on January 1st, Webb is showing us events from the first week of January. Hubble could see into late January or early February. Webb pushed back the curtain to those first, formative days when the universe was still finding its shape. The image itself is visually stunning. Thousands of galaxies, each containing billions of stars, spread across the frame in a tapestry of light and color. Some appear as clear spirals or ellipses. Others are smeared and distorted by gravitational lensing, their light bent around massive foreground galaxy clusters. Some are mere red dots, so distant and ancient that their light has been stretched into the infrared by the universe's expansion. And what Webb revealed in those earliest epochs has left astronomers genuinely puzzled. According to our models of galaxy formation, early galaxies should be small, messy, and irregular. They're supposed to be the building blocks that, over billions of years, merge and grow into the grand spiral and elliptical galaxies we see in the modern universe. Think of them as cosmic teenagers, awkward, still developing, not yet mature. But that's not what Webb found. Instead, Webb has revealed massive, mature-looking galaxies existing far earlier than our theories predicted. We're talking about galaxies with masses equivalent to hundreds of billions of suns, with structures that look surprisingly organized and developed, existing when the universe was supposedly too young for such objects to have formed. One particularly troubling example is a galaxy designated JWST Z14-0, observed as it appeared roughly 290 million years after the Big Bang. This galaxy is not only surprisingly bright, but spectroscopic analysis suggests it contains an unexpected abundance of heavier elements that should take multiple generations of stars to produce. But there hasn't been enough time for multiple stellar generations. It's like finding a fully furnished mansion standing in what should be an empty field. Another galaxy, Sears 93316, initially appeared to exist just 235 million years after the Big Bang. If confirmed, it would push back our understanding of when galaxies could form to even earlier times. While subsequent analysis suggested this galaxy might not be quite as distant as first thought, the broader pattern remains. Webb is finding well-developed galaxies earlier than we expected. This has triggered what some astronomers are calling a cosmological crisis. Our standard model of cosmology, the lambda CDM model that has successfully explained so much about the universe's evolution, is being stress-tested in ways we never anticipated. Some researchers have suggested we might need to modify our understanding of how quickly structures could form in the early universe. Others wonder if there are unknown physics at play in those earliest eras, processes that could accelerate galaxy formation beyond what we currently believe possible. A few scientists have even proposed more radical solutions. Perhaps our understanding of dark matter is incomplete, or perhaps the cosmological constant, the value describing dark energy, was different in the early universe. These would be fundamental changes to our cosmological model, affecting not just galaxy formation, but our entire understanding of how the universe evolved. But let's be clear, this isn't a crisis in the sense of cosmology being wrong. It's a crisis in the best possible way. Our observations are outpacing our theories, forcing us to refine and improve our understanding. This is exactly how science is supposed to work. But Webb's revelations don't stop with early galaxies. The telescope's infrared vision allows it to peer through cosmic dust clouds that completely block visible light. This capability has given us unprecedented views into stellar nurseries, regions where new stars are being born. Take the Carina Nebula, one of the first targets Webb observed. Located about 7,600 light-years from Earth, this is one of the largest and brightest nebulae in our sky, a vast star-forming region in the southern constellation Carina. Hubble had previously imaged this region, revealing towering pillars of gas and dust sculpted by radiation from young, massive stars. The Hubble image was already breathtaking, showing cosmic cliffs of gas illuminated by ultraviolet light from newborn stars. Webb's view of the same region is almost unrecognizable. Where Hubble showed us the surface of the cloud glowing in visible light, Webb sees through it, revealing hundreds of previously hidden stars and protostars, baby stars still cocooned in their birth material. The infrared view transforms the Carina Nebula into a landscape of extraordinary depth and complexity. In Webb's image, the cosmic cliffs, the edge of a massive gas cloud, appear as a jagged mountain range backlit by countless stars. But these aren't mountains of rock. They're walls of gas and dust being eroded by intense radiation from young stars. At the peaks of these cliffs, we can see jets of material being ejected from forming stars, visible as fountains of gas shooting into space. These jets are a key part of the star formation process, carrying away excess angular momentum and allowing material to continue falling onto the growing protostar. In the Pillars of Creation, that iconic Hubble image that became perhaps the most famous astronomical photograph ever taken, Webb's infrared vision reveals a landscape that looks alien and beautiful in completely new ways. The pillars themselves appear more translucent, almost ghostly, their internal structure visible in a way that Hubble couldn't show. Countless stars invisible to Hubble pepper the scene, many of them extremely young, still surrounded by the remnants of the disks from which they formed. At the tips of the pillars, where new stars are just beginning to ignite, Webb captures knots of dense gas glowing in infrared light, the literal moment of stellar birth captured in unprecedented detail. We can see protostars that haven't even fully formed yet, objects that are still gathering mass from their surroundings, not yet hot enough to begin fusion. These are stars in their earliest infancy, objects we could never see before Webb. These observations are already changing our understanding of star formation. We can now see protostars at earlier stages than ever before, track how material falls onto forming stars, and observe the complex interplay between stellar radiation and the surrounding gas and dust. It's like having a window into the cosmic maternity ward, watching the universe's stars being born in real time. Then there are the exoplanets, planets orbiting stars other than our Sun. Webb wasn't primarily designed as an exoplanet observatory, but it has proven remarkably capable in this arena. Unlike most exoplanet detection methods, which simply confirm that a planet exists, Webb can actually study these worlds in detail by analyzing the light that passes through their atmospheres. When an exoplanet transits in front of its star from our perspective, some of the star's light filters through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb specific wavelengths of light, creating a kind of chemical fingerprint. Webb's sensitive spectrographs can decode these fingerprints, revealing what gases are present in alien atmospheres. In its first year of operation alone, Webb detected carbon dioxide in the atmosphere of WSP-39b, a gas giant exoplanet about 700 light-years away. This was the first clear detection of carbon dioxide in an exoplanet atmosphere, a milestone in the study of alien worlds. It found water vapor, sodium, and potassium in the atmosphere of WSP-96b, another hot Jupiter. It observed weather patterns on these hot Jupiters, detected clouds on some worlds, and found atmospheres that were chemically different from anything we'd predicted. One particularly surprising finding came from observations of WSP-96b. This planet, about half the mass of Jupiter and located 150 light-years away, shows clear signs of water vapor and clouds in its atmosphere. But the clouds aren't made of water ice like clouds on Earth. They're likely composed of silicates, essentially rock vapor condensing in the scorching atmosphere of this gas giant. The planet's atmosphere is so hot that minerals vaporize and then condense into tiny droplets, forming clouds of liquid rock. Perhaps most intriguingly, Webb has begun studying smaller, rocky worlds, planets more similar to Earth. While we haven't yet found a perfect Earth twin, Webb is building up a catalogue of rocky planet atmospheres, searching for biosignature gases that might indicate the presence of life. One target of particular interest is the TRAPPIST-1 system, a collection of 7 Earth-sized planets orbiting a small, cool star about 40 light-years away. At least 3 of these planets orbit in the habitable zone, the region where liquid water could exist on a planet's surface. Early Webb observations have already ruled out thick hydrogen atmospheres on some of these worlds, narrowing down the possibilities and helping scientists focus their search. The observations of TRAPPIST-1c, for instance, revealed essentially no atmosphere, or at most, a very thin one. The intense radiation from the star, combined with the planet's proximity, has likely stripped away any thick atmosphere it might have once had. This is crucial information because it suggests that planets around red dwarf stars, the most common type of star in the galaxy, might face challenges maintaining atmospheres which would impact their habitability. What we're learning is that planetary atmospheres are far more diverse than our solar system suggested. We have hot Jupiters with atmospheres being stripped away by stellar radiation. We have planets with clouds made of silicates, basically rocks condensing in the atmosphere. We have worlds with temperature extremes that challenge our understanding of atmospheric chemistry. We have planets that might be ocean worlds, planets that might be massive versions of Earth, and planets unlike anything in our solar system. Each observation reveals a universe more varied, more complex, and more surprising than we anticipated. But perhaps the most profound thing Webb has shown us is just how much there is to see. In every direction Webb points, in every deep field it captures, there are galaxies, thousands upon thousands of them stretching back through cosmic time. And in many of those galaxies we can see individual features: spiral arms, star-forming regions, supermassive black holes at their centers glowing as they consume matter. We're not just seeing more of the universe, we're seeing it in a way that reveals layers of complexity we never knew existed. And with each new observation, the universe becomes both more familiar and more strange. A place governed by the same physics we observe on Earth, yet playing out in ways that continually surprise and challenge us. The universe that Webb is unveiling is not the universe we expected to find, and we're only just beginning to understand what that means. At the heart of nearly every large galaxy, something immense lurks in the darkness, a region where gravity has become so intense that not even light can escape. These are supermassive black holes, objects containing millions or even billions of times the mass of our Sun, compressed into a region smaller than our solar system. For decades we've known these cosmic monsters exist. We've observed their effects on nearby stars, watching them orbit at tremendous speeds around seemingly empty points in space. We've seen jets of matter and energy erupting from the regions around black holes, powered by material falling in and heating to millions of degrees. We've even captured images of the glowing accretion disks surrounding them, including the famous image of the supermassive black hole at the center of the galaxy M87, taken by the Event Horizon Telescope. But their origins have remained mysterious. How did such massive objects form? Were they present in the earliest galaxies, or did they grow over time? And how do they influence the evolution of their host galaxies? Webb is helping us answer these questions, and once again, the answers are not what we expected. According to conventional theory, supermassive black holes should grow gradually. It starts with the death of a massive star, at least 20 or 30 times the mass of the Sun, which collapses into a stellar mass black hole weighing perhaps 10 to 100 times the mass of the Sun. Over billions of years, this black hole feeds on surrounding material and merges with other black holes, slowly growing to supermassive proportions. The problem is the timeline. This gradual growth process takes time, billions of years. Yet Webb has discovered quasars, the brilliant beacons powered by actively feeding supermassive black holes, existing when the universe was less than 1 billion years old. Some of these black holes already contain 1 billion solar masses. The math simply doesn't work. There hasn't been enough time for these black holes to grow from stellar mass seeds to supermassive proportions through normal feeding and mergers. Even if these black holes were feeding at the maximum possible rate, the Eddington limit, where the radiation pressure from infalling matter balances gravity, They couldn't have grown this large this quickly. It's like planting an acorn and finding a 100-foot oak tree a year later. The growth rate required simply exceeds what we thought was possible. This has led to a proliferation of alternative theories. Perhaps some supermassive black holes formed directly in the early universe, when clouds of primordial gas collapsed straight into black holes without ever forming stars. These direct collapse black holes could start with masses of thousands or even hundreds of thousands of solar masses, giving them a head start on their growth to supermassive status. Perhaps the feeding rate in the early universe was far more efficient than we thought. Maybe the conditions in early galaxies, denser gas, more turbulent dynamics, allowed black holes to grow faster than current models predict, perhaps even exceeding the Eddington limit under certain circumstances. Or perhaps there are physical processes we simply don't understand yet, mechanisms that could accelerate black hole growth in the extreme conditions of the young universe. Some theorists have proposed that black holes might merge more frequently in the early universe, or that they might capture dense star clusters whole, rapidly adding mass. Webb's observations are providing crucial data to test these theories. By studying the properties of these early quasars, their brightness, the composition of material falling into them, the relationship between black hole mass and the surrounding galaxy, scientists are piecing together a new understanding of how these cosmic giants came to be. One particularly interesting observation involves a quasar designated J0313 1806, which Webb has studied in detail. This object existed when the universe was only about 670 million years old, and it harbors a black hole with a mass of about 1.6 billion times that of the Sun. Not only does this black hole exist impossibly early, but it appears to be growing incredibly rapidly, consuming matter at a rate far exceeding what we thought possible. Even more puzzling, the galaxy hosting this quasar shows signs of intense star formation, producing new stars at a rate of hundreds of solar masses per year. This suggests a complex relationship between black hole growth and galaxy evolution. The black hole isn't just sitting there consuming matter, it's actively influencing the formation of stars in its host galaxy. But black holes are only one part of the cosmic mystery. The other, even more perplexing, is dark matter. Here's a peculiar fact about the universe: the stuff we can see, stars, planets, gas clouds, even black holes, makes up only about 15% of all matter. The other 85% is something else entirely, something that doesn't emit, absorb, or reflect light. We call it dark matter, and it remains one of the most profound mysteries in physics. We know dark matter exists because we can see its gravitational effects. Galaxies rotate too fast for the visible matter they contain. Based on the stars and gas we can see, galaxies should fly apart as they spin, but something invisible is holding them together with its gravity. Galaxy clusters contain far too little visible mass to explain their gravitational lensing effects, the way they bend light from background objects. The motions of galaxies within clusters are too fast for the visible matter alone to keep them bound. Computer simulations of the universe's evolution only match observations if we include vast quantities of invisible matter, providing gravitational scaffolding for normal matter to clump around. Without dark matter in the simulations, galaxies don't form when or where we observe them, and the large-scale structure of the universe looks completely different from what we see. But what is dark matter? We don't know. We know what it isn't. It's not normal matter, not antimatter, not black holes in any conventional sense. It doesn't interact with light. It doesn't interact with normal matter except through gravity. Decades of experiments searching for dark matter particles have come up empty, placing increasingly tight constraints on what dark matter could be without actually detecting it. It's like trying to understand a sculpture you can only touch in complete darkness. You can feel its shape and weight, trace its contours, measure its mass, but you have no idea what it's made of or what it looks like. Webb is approaching this mystery from a unique angle. While it can't directly observe dark matter, nothing can, it can map how dark matter is distributed throughout the universe by observing gravitational lensing. Gravitational lensing occurs when the gravity of a massive object, like a galaxy cluster containing vast amounts of dark matter, bends the light from more distant objects. Einstein's general theory of relativity predicts this effect. Massive objects warp the fabric of space-time, and light follows the curvature of that warped space-time, bending its path. This creates distorted, often multiple images of background galaxies, smeared and warped by the intervening gravity. Sometimes we see Einstein, rings, perfect or nearly perfect circles of light from a background galaxy that has been gravitationally lensed by a foreground object. Sometimes we see elongated arcs or multiple distorted images of the same galaxy scattered across the field of view. By carefully analyzing these distortions, astronomers can create maps of where mass exists, including the invisible dark matter. The technique is called gravitational lensing tomography, and it's one of the most powerful tools we have for studying dark matter distribution. Webb's sensitivity and resolution allow it to detect gravitational lensing effects with unprecedented precision. It can see fainter, more distant background galaxies being lensed, and it can resolve finer details in the lensing patterns. This is helping scientists create ever more detailed maps of dark matter distribution, from the cosmic web of dark matter filaments connecting galaxy clusters to the dark matter halos surrounding individual galaxies. These maps are revealing structure in the dark matter distribution. It's not uniformly spread, but forms webs and clumps, exactly as computer simulations predicted. This confirms that our general picture of dark matter is probably correct, even if we don't know what it's made of. The dark matter appears to form the skeleton of cosmic structure, with normal matter collecting in the densest regions where dark matter has accumulated. But the maps also reveal tensions between observations and predictions, hints that our models might need refinement. Some galaxy clusters show dark matter distributions that don't perfectly match what simulations predict. Some galaxies appear to have dark matter halos with different properties than the standard model suggests. These discrepancies might point to subtle aspects of dark matter physics we haven't yet understood, or they might indicate that our simulations need to include additional physics to match reality. And then there's dark energy, which is somehow even stranger than dark matter. In 1998, astronomers made a shocking discovery. The universe's expansion is accelerating. For most of cosmic history, everyone assumed that the universe's expansion, set in motion by the Big Bang, should be slowing down due to the gravitational attraction of all the matter in the universe. But observations of distant supernovae revealed that the expansion is actually speeding up. Something is pushing the universe apart, overcoming gravity and causing the expansion to accelerate. We call this mysterious force dark energy, and it makes up about 68% of the total energy content of the universe. Combined with dark matter at 27%, dark energy means that the ordinary matter we're familiar with, everything we can see and touch, all the stars and planets and galaxies, makes up only about 5% of the universe. We live in a universe where 95% of the content is completely mysterious to us. Webb isn't primarily designed to study dark energy, but it's contributing to our understanding nonetheless. By observing extremely distant supernova and galaxies, Webb is helping to chart the expansion history of the universe with greater precision. These observations will help determine whether dark energy is constant throughout cosmic time, a cosmological constant as Einstein proposed, or whether it changes in strength over billions of years, which would indicate something more complex called quintessence. Early hints from Webb observations, combined with data from other sources, suggest there might be tensions in our cosmological model. Different methods of measuring the universe's expansion rate are giving slightly different answers, a puzzle known as the Hubble tension. Some measurements suggest the universe is expanding at about 67 kilometers per second per megaparsec, while others suggest about 73. This might not sound like a big difference, but it's statistically significant and has persisted despite increasingly precise observations. Some researchers wonder if this points to new physics, perhaps a variation in dark energy over time, or an unknown component of the cosmos we haven't yet identified, or even a fundamental misunderstanding in how we measure cosmic distances. Others think the discrepancy might eventually be resolved through better calibration of our measurement methods. What's becoming clear is that the universe is far more complex than visible matter alone would suggest. We live in a cosmos where 95% of the content, dark matter and dark energy combined, is completely mysterious to us. We can map its effects, we can include it in our models, we can predict how it should behave, but we still don't know what it actually is. Webb is giving us better observations, sharper images, and more detailed data than ever before. But in doing so, it's also highlighting just how much we don't understand. The black holes that shouldn't exist, the dark matter we can't identify, the dark energy pushing the universe apart. These aren't minor gaps in our knowledge. They're fundamental questions about the very nature of reality. And that's exactly what makes this such an exciting time in cosmology. We're not just filling in details on a mostly complete picture. We're discovering that the picture is far larger and stranger than we ever imagined, that the universe operates according to principles we're only beginning to grasp. The cosmos is revealing itself to be a place of profound mystery, and Webb is our guide into that mystery. There is perhaps no process more fundamental to the existence of life than the formation of stars and planets. Every atom in your body, except for hydrogen, was forged in the nuclear furnaces of ancient stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, the carbon that forms the backbone of every organic molecule in your cells, all of it created in stellar cores and scattered across space when those stars died. We are quite literally made of stardust. Understanding how stars and planets form is therefore understanding our own origins. And Webb is giving us a front row seat to this cosmic creation story. Star formation begins in giant molecular clouds, vast regions of space filled with hydrogen gas and dust. These clouds can span hundreds of light years and contain enough material to create thousands or even millions of stars. They're cold, typically only about 10 to 20 degrees above absolute zero, and they're the darkest places in the galaxy, blocking even the light of background stars. Within these clouds, small density fluctuations can trigger collapse. Perhaps a nearby supernova sends a shockwave through the cloud. Perhaps two clouds collide. Perhaps the cloud simply becomes dense enough that its own gravity overcomes the internal pressure supporting it. Whatever the trigger, once a region starts collapsing, it accelerates. Gravity pulls material inward, the region becomes denser, gravity becomes stronger, and the collapse continues. For most of history, studying these stellar nurseries was nearly impossible. The very dust that forms the raw material for stars also blocks visible light, hiding the action from telescopes like Hubble. We could see the outer edges of molecular clouds, illuminated by nearby stars, but the dense cores where stars actually form remained invisible. But infrared light passes through dust relatively easily, and that's where Webb excels. When we point Webb at star-forming regions, we're seeing through the cosmic curtain, penetrating deep into the cores of molecular clouds to witness star formation in progress. Take the Orion Nebula, one of the most studied objects in astronomy. Located about 1,350 light-years from Earth, it's the closest major star-forming region to us, a cosmic laboratory where we can study stellar birth in detail. The nebula is visible to the naked eye as a fuzzy patch in Orion's sword, and through telescopes it reveals itself as a glowing cloud of gas, illuminated by the radiation of young, hot stars. Hubble revealed the Orion Nebula's glowing gas and the brightest young stars, creating images of extraordinary beauty showing billowing clouds, pillars of gas and dust, and the brilliant stars of the trapezium cluster at the nebula's heart. But Hubble could only see the surface, the regions where visible light could penetrate. Webb's view of the same region is transformative. In Webb's images, the Orion Nebula becomes a landscape of unprecedented complexity. We can see deep into the densest cores of the cloud where new stars are igniting. We observe protostars, objects that are gathering mass but haven't yet become hot enough to begin fusion, in stages of development we've never witnessed before. Around many young stars we can detect protoplanetary disks, the swirling pancakes of gas and dust from which planets form. The level of detail is extraordinary. We can see individual forming stars surrounded by cocoons of gas and dust. We can observe jets of material being ejected from stellar poles, high-velocity outflows that carry away angular momentum and allow material to continue falling onto the growing protostar. These jets can extend for light years, ploughing into the surrounding gas and creating shockwaves that glow in infrared light. But it's not just about seeing deeper. Webb's spectroscopic capabilities allow it to analyze the chemistry of these regions with exquisite precision. We can identify specific molecules in the gas and dust, track their abundances, and watch how chemistry evolves as stars form. This has revealed something fascinating. Star-forming regions are chemical factories. As gas collapses under gravity and heats up, new molecules form through a complex web of chemical reactions. Simple molecules like carbon monoxide and water form first. Then more complex organic chemistry emerges. Molecules containing carbon-hydrogen bonds, the fundamental building blocks of organic chemistry. Webb has detected water, carbon dioxide, methane, ammonia, formaldehyde, methanol, and even more complex organic molecules in protoplanetary disks. These include polycyclic aromatic hydrocarbons, ring-shaped carbon molecules, and even simple sugars. The raw materials for life, the chemical building blocks that would eventually be incorporated into amino acids and nucleotides, and all the other molecules essential for biology, are literally present at the birth of planetary systems. This is profound. It means that the chemistry necessary for life doesn't have to develop after planets form. It's already there from the beginning, baked into the material from which planets are made. The traditional picture of planet formation goes something like this. Around a young star, a disk of gas and dust rotates. This protoplanetary disk is a remnant of the cloud from which the star formed, material that didn't fall onto the star itself, but remained in orbit around it. Small dust grains in this disk, particles microscopic or perhaps millimeter-sized, collide as they orbit. Sometimes they stick together through electrostatic forces or molecular attraction. Gradually, these collisions build up larger and larger objects. These growing bodies, now perhaps centimeter or meter-sized, continue to collide and merge. This process, called accretion, continues through various stages. Meter-sized objects become kilometer-sized planetesimals, rocky or icy bodies that are now massive enough that their gravity helps them continue growing. Planetesimals collide and merge over millions of years, eventually forming planetary embryos, objects perhaps the size of Earth's moon or Mars. Finally, these embryos collide in catastrophic impacts, forming the terrestrial planets we know. In our solar system, this process created Mercury, Venus, Earth, and Mars. The collision that formed Earth's moon was one of these giant impacts, when a Mars-sized object slammed into the proto-Earth, ejecting material that coalesced into the moon. For gas-giant planets like Jupiter, the process is similar at first, but with a crucial difference. Once a rocky core reaches about 10 times Earth's mass, it becomes massive enough to gravitationally capture vast amounts of hydrogen and helium from the surrounding disk, puffing up into a gas giant. This runaway gas accretion continues until the disk is depleted or dispersed. This model works reasonably well for our solar system, but Webb is showing us that planet formation is far more diverse and complex than this standard picture suggests. Consider the system around the star PDS 70, located about 370 light-years away. This young star, only about 5 million years old, a mere infant in cosmic terms, has a disk with a large gap. This gap is a telltale sign that planets are forming, sweeping up material in their orbits and clearing lanes through the disk. And in that gap, Webb can actually see 2 planets, not just infer their presence from the gap structure, but actually detect them directly. These planets are still actively forming, accreting material from the surrounding disk. Webb's observations reveal that these forming planets are surrounded by their own disks of material, circumplanetary disks, that may be forming moons even as the planets themselves coalesce. This is planet formation happening in real time, on timescales we can observe. Every observation of PDS 70 adds new data about how planets grow, how they interact with their birth disk, how they might form satellite systems. Webb has also studied more mature protoplanetary disks, revealing complex structures that hint at unseen planets. Spiral patterns in the disk, created by gravitational interactions between planets and the disk. Gaps and rings where planets have cleared material from certain orbital distances. Asymmetries and clumps, possibly indicating concentrations of material that might themselves be collapsing into planets. All of these features are thought to be carved by planets interacting gravitationally with the disk material. By studying these patterns, astronomers can infer the presence of planets too small or faint to detect directly and understand how planets reshape their birth environments. It's like being a detective, examining footprints in the snow to deduce what left them, even if you can't see the animal itself. What's emerging is a picture of planet formation as a chaotic, dynamic process. Planets don't just form in isolation and stay put. They migrate through the disk, moving inward or outward due to gravitational interactions with the disk and with other planets. They can scatter each other into highly elliptical orbits. They can even eject each other from the system entirely, sending planets careening into interstellar space to wander the galaxy as rogue worlds. The final architecture of a planetary system is the result of this complex gravitational dance, with planets jockeying for position during the first few million years until the disk disperses and the system settles into its final configuration. This helps explain some of the bizarre exoplanet systems Webb and other telescopes have discovered. Hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun, with orbital periods of just a few days, probably didn't form there. Gas giants require large amounts of hydrogen and helium, which only exist in the outer, colder regions of protoplanetary disks. These planets likely formed farther out and migrated inward, possibly through gravitational interactions with the disk or with other planets. Super-Earths and mini-Neptunes, planets with sizes between Earth and Neptune, a category with no analogue in our solar system but common elsewhere, might form through different processes or in different disk conditions than the planets we know. Some might be rocky worlds that captured small atmospheres. Others might be water worlds, covered entirely by deep oceans. Still, others might have thick hydrogen atmospheres despite being rocky underneath. Webb is also revealing diversity in the disks themselves. Some are massive and long-lived, persisting for millions of years, and potentially forming many planets. These disks have enough material to create entire solar systems like our own. Others are wispy and short-lived, dissipating before significant planet formation can occur, perhaps creating only a few small, rocky worlds, or no planets at all. The composition varies too. Some disks are rich in water and organic molecules. Others are drier and more rocky. This depends on factors like the disk's temperature, which is set by the star's luminosity, and its initial composition inherited from the molecular cloud from which the star formed. This chemical diversity has profound implications for the types of planets that can form. A water-rich disk might produce ocean worlds, planets entirely covered in water, with global oceans hundreds of kilometers deep. A disk rich in carbon might produce planets with exotic carbon-based geology, perhaps with surfaces of graphite or diamond, or atmospheres rich in carbon dioxide and carbon monoxide. The composition of the disk sets the composition of the planets, which in turn influences what kind of atmospheres they can develop and whether they might support life. A planet rich in water and organic molecules from birth has a better chance of developing the chemistry necessary for life than a dry, rocky world formed from depleted disk material. One of Webb's most intriguing contributions is its study of brown dwarfs, objects too massive to be planets but too small to sustain hydrogen fusion like stars. These failed stars, typically with masses between 13 and 75 times that of Jupiter, blur the line between planets and stars, and they represent an interesting test case for our theories of formation. Webb has discovered that some brown dwarfs have their own disks of material, similar to the protoplanetary disks around young stars. This raises a fascinating question. Can planets form around brown dwarfs the way they form around stars? Early observations suggest yes. We might live in a universe where planets can form not just around stars, but around brown dwarfs, and possibly even around more exotic objects. A planet orbiting a brown dwarf would receive little light and heat. The brown dwarf would glow only faintly in infrared, but it could still have geological activity. Perhaps even a subsurface ocean kept liquid by tidal heating, similar to Jupiter's moon Europa. The diversity of planetary systems could be far greater than we ever imagined. Not just planets around sun-like stars, but planets around red dwarfs, around massive blue stars, though these live short lives, around binary star systems, around brown dwarfs, perhaps even orphan planets drifting through interstellar space, ejected from their birth systems. What ties all of this together is the realization that planet formation is not a rare or unusual process. It's a natural consequence of star formation. Nearly every star forms with a disk, and in nearly every disk, the process of building planets likely begins. Whether those planets survive, whether they end up in stable orbits or get ejected, whether they're large or small, rocky or gaseous, these details vary. But the fundamental process of turning disk material into planets appears to be universal. The universe is quite possibly teeming with planetary systems, each shaped by the unique conditions of its birth, each following the same basic physical processes, but yielding different outcomes based on initial conditions and random chance. And among those countless worlds, some will have the right conditions for something extraordinary to emerge. Life. The formation of stars and planets is not just an astronomical process. It's the mechanism by which the universe organizes itself, creating complexity from chaos, building worlds from clouds of gas. It's the process that made Earth possible, that made you possible. It's the bridge between the Big Bang and biology, between primordial hydrogen and human consciousness. And now, for the first time, we can watch it happen. We can observe stars being born, planets coalescing, chemistry complexifying. We can trace the path from molecular cloud to planetary system, understanding each step with unprecedented clarity. Webb has given us this gift, the ability to witness cosmic creation, to see our own origins playing out around distant stars. And with each observation, we understand a little more about how we came to be, about our place in the cosmic story, about the processes that made life possible. Are we alone in the universe? This question has haunted humanity for as long as we've been capable of asking it. Every culture throughout history has wondered whether life exists beyond Earth, whether we're a unique cosmic accident or one instance of a universal phenomenon. Ancient philosophers debated whether the stars were other suns with their own worlds. Medieval scholars wondered if God had created life elsewhere in his vast creation. Science fiction writers have populated the cosmos with aliens of every imaginable form. For most of human history, this question was purely philosophical. We had no way to investigate it scientifically. We couldn't even prove that other planets existed beyond our solar system, let alone study them for signs of life. But in recent decades, that's changed dramatically. We've discovered that the universe is filled with planets, billions of them in our galaxy alone. We've learned that the chemistry of life relies on common elements found throughout the cosmos: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. We've found that life on Earth can survive in extreme environments we once thought uninhabitable. Boiling hot springs, Antarctic ice, deep ocean trenches, acidic lakes, even inside nuclear reactors. And now, with Webb, we have a tool that might actually detect signs of life on worlds orbiting distant stars. The search for extraterrestrial life takes several forms. There's the search for microbial life in our own solar system, particularly on Mars or the icy moons of Jupiter and Saturn. There's the search for extraterrestrial intelligence, or SETI, which listens for radio signals that might indicate technological civilizations. And there's the study of exoplanet atmospheres, looking for biosignatures, chemical signs that life might be present. This last approach is where Webb truly shines. When we look at Earth from space, our planet's atmosphere tells a story. The composition of our atmosphere is deeply unusual from a pure chemistry standpoint. We have large amounts of oxygen, about 21% of the atmosphere, coexisting with methane, even though these gases react with each other. In a lifeless Earth, this wouldn't be possible. Oxygen is highly reactive. It would quickly combine with methane, with hydrogen, with minerals on the surface, depleting itself from the atmosphere in a geologically short time. The fact that our atmosphere maintains high oxygen levels requires constant replenishment. On Earth, that replenishment comes from life. Photosynthetic organisms, plants, algae, cyanobacteria, produce oxygen as a byproduct of converting carbon dioxide and water into sugars. Various life forms produce methane through metabolism. Life is constantly pumping these gases into the atmosphere, maintaining the chemical imbalance we observe. This is the concept of a biosignature, a chemical or combination of chemicals in a planet's atmosphere that would be difficult to explain without the presence of life. If we could detect such signatures in the atmosphere of an exoplanet, it would be strong evidence, though not definitive proof, that life exists there. The challenge is that no single gas is a perfect biosignature. Oxygen can be produced by non-biological processes, such as the photodissociation of water molecules by ultraviolet light. Methane can bubble up from geological processes. Even more exotic gases that we associate with life could potentially be produced by unusual chemistry or geology. This is why astrobiologists look for combinations of gases, patterns that would be very hard to explain without biology. Oxygen and methane together. Oxygen with the presence of water vapor and carbon dioxide suggesting an active carbon cycle. Seasonal variations in atmospheric composition indicating biological activity responding to changing conditions. Webb is designed to detect and characterize exoplanet atmospheres through a technique called transmission spectroscopy. The principle is elegant. When a planet passes in front of its star from our perspective, an event called a transit, a tiny fraction of the star's light, filters through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb different wavelengths of light. Oxygen absorbs certain wavelengths in the visible and near-infrared. Carbon dioxide has strong absorption features in the infrared. Water vapor, methane, ozone, each has its own spectral fingerprint. Webb's sensitive spectrographs can measure the star's light during a transit and compare it to the light when the planet is not transiting. The difference reveals what wavelengths were absorbed by the planet's atmosphere, allowing scientists to decode what gases are present. In its first years of operation, Webb has already demonstrated this capability with remarkable success. The detection of carbon dioxide in WSP-39b's atmosphere was groundbreaking. The first unambiguous detection of this molecule in an exoplanet atmosphere. The discovery of water vapor, clouds, and hazes in various hot Jupiters has revealed that giant planet atmospheres are far more complex than simple models suggested. But these are gas giants, and while scientifically fascinating, they're not candidates for life as we know it. Life requires solid surfaces or liquid environments, stable temperatures, and certain chemical conditions. Gas giants, with their extreme temperatures, crushing pressures, and lack of solid surfaces, aren't habitable in any way we understand. The real excitement comes from rocky planets, worlds more like Earth. One of the most intriguing targets is the TRAPPIST-1 system. Discovered in 2015 and confirmed to have 7 Earth-sized planets in 2017, this system is extraordinary. All 7 planets are similar in size to Earth, and at least 3 of them, TRAPPIST-1e, F, and G, orbit in the habitable zone, the region where surface temperatures could allow liquid water to exist. The star itself, TRAPPIST-1, is an ultra-cool red dwarf, much smaller and cooler than our Sun. This means its habitable zone is very close in. The planets orbit much closer to their star than Mercury orbits the Sun. But because the star is so cool, these close-in planets receive roughly the same amount of energy as Earth receives from the Sun. Early Webb observations of TRAPPIST-1 planets have already yielded crucial results. Observations of TRAPPIST-1b, the innermost planet, revealed essentially no atmosphere or, at most, a very thin one. The intense radiation from the star, combined with the planet's proximity and likely lack of a strong magnetic field, has probably stripped away any thick atmosphere it might have once had. This is important information. It suggests that planets around red dwarf stars, which make up about 75% of all stars in the galaxy, might face challenges maintaining atmospheres. Red dwarfs are known for powerful flares and intense ultraviolet and X-ray radiation, especially when young. This radiation can strip atmospheres from nearby planets, potentially making them uninhabitable even if they're in the habitable zone in terms of temperature. But not all TRAPPIST-1 planets may have lost their atmospheres. The outer planets, particularly TRAPPIST-1, F, and G, are farther from the star and might have retained their atmospheres, especially if they have magnetic fields to shield them from stellar radiation. Webb will continue studying these planets, searching for signs of atmospheres and, if atmospheres are present, analyzing their composition. Scientists are particularly interested in looking for water vapor, carbon dioxide, methane, and oxygen. The ideal biosignature would be multiple gases in combination that would be very hard to explain without life. For instance, if we detected oxygen and methane together in TRAPPIST-1e's atmosphere, that would be intriguing. If we also detected water vapor and the oxygen levels were high enough that non-biological processes seemed unlikely to produce them, that would be even more compelling. If we observed seasonal variations in these gases, suggesting biological activity responding to orbital and climate cycles, that would be stronger still. The challenge is patience and precision. These signals are incredibly faint. The light from the star is millions of times brighter than the tiny atmospheric signal we're trying to detect. Separating the signal from the noise requires multiple observations, careful calibration, and sophisticated data analysis. But Webb is up to the task. With enough observing time, it can build up detailed spectral profiles of rocky planet atmospheres, searching for those telltale signs of life. Beyond TRAPPIST-1, there are other fascinating targets. Proxima Centauri b, the closest known exoplanet to Earth at just 4.2 light-years away, orbits in the habitable zone of its red dwarf star. If it has an atmosphere, a big if, given the intense stellar activity of Proxima Centauri, Webb could potentially study it. LHS 1140b, another planet orbiting a red dwarf about 40 light-years away, might be a water world, a planet covered entirely by a deep global ocean. If it has an atmosphere with water vapor and other gases, Webb might be able to detect them. And there are planets around Sun-like stars too. These are harder to study. They orbit farther from their stars, making transits rarer and atmospheric signals weaker. But they're crucial targets. A rocky planet in the habitable zone of a Sun-like star might be the best candidate for life as we know it, without the complications of intense stellar activity that red dwarfs present. One fascinating possibility that Webb might stumble upon is techno-signatures, signs of technological civilization. While Webb isn't specifically designed for this, it could potentially detect atmospheric pollution or industrial chemicals that would be hard to explain naturally. Chlorofluorocarbons, for instance, are entirely synthetic on Earth, created only by industrial processes for use in refrigeration, aerosols, and other applications. They don't occur naturally anywhere on Earth, and they're very long-lived in the atmosphere. If we detected CFCs in an exoplanet's atmosphere, it would be a stunning indication of technological activity. Similarly, high levels of nitrogen dioxide, which on Earth comes primarily from combustion and industry, might indicate technological civilization. Or unusual ratios of gases that suggest artificial production rather than natural processes. These scenarios are speculative, and the likelihood of detecting techno-signatures with Webb is low. We'd need to happen to observe a planet with a technological civilization at roughly our level or beyond, and the chemicals they use would need to be detectable in their atmosphere. But it's not impossible. The search for life extends beyond exoplanets to our own solar system as well. Webb has studied Mars, analyzing its thin atmosphere and surface composition. While Mars is too cold and dry to support life on its surface today, it might have been habitable billions of years ago, and microbial life might still exist in subsurface environments. Webb's observations of Mars focus on atmospheric chemistry and surface mineralogy, looking for organic molecules or other signs that the planet once supported life. These observations complement rover and lander missions on the Martian surface, providing a global perspective that ground-based missions can't achieve. But perhaps the most tantalizing targets for life in our solar system are the icy moons of the outer planets: Europa, Enceladus, and Titan. Europa, a moon of Jupiter, is covered in ice, but beneath that ice lies a global ocean that might contain twice as much water as all of Earth's oceans combined. Tidal heating from Jupiter, the moon being constantly flexed and squeezed by Jupiter's gravity as it orbits, keeps this ocean liquid despite Europa's location far from the sun. And where there's liquid water, there might be life. On Earth, we find life anywhere there's liquid water, even in extreme environments like deep ocean hydrothermal vents, where no sunlight penetrates and organisms rely on chemical energy from volcanic activity. Europa's subsurface ocean might have similar hydrothermal vents, providing energy and nutrients for potential life. Webb can study Europa's surface, looking for organic molecules and mapping the composition of material that might have erupted from the subsurface ocean through cracks in the ice. While it can't see beneath the ice, it can analyze what the ocean might contain by studying what gets deposited on the surface. If Webb detects complex organic molecules or unusual chemical signatures, it would strengthen the case for Europa's ocean being habitable. Enceladus, a small moon of Saturn, is in some ways even more accessible for study. This icy world has geysers that shoot water vapor and ice particles from its subsurface ocean directly into space through cracks at its south pole. These plumes give us direct access to ocean material without needing to drill through miles of ice. The Cassini spacecraft flew through these plumes multiple times, analyzing their composition and discovering organic molecules, salts, and evidence of hydrothermal activity. Webb is continuing this work, using its spectroscopic capabilities to analyze the plume's chemistry in greater detail. If life exists in Enceladus's ocean, it's possible that biological molecules or even microorganisms might be present in the plumes, expelled from the ocean and shot into space. While Webb can't detect individual microbes, it might be able to detect complex organic molecules or unusual chemical ratios that would suggest biological activity. Then there's Titan, Saturn's largest moon, which is one of the strangest worlds in our solar system. Titan has a thick nitrogen atmosphere, thicker than Earth's, and is the only world besides Earth known to have stable liquid on its surface. But Titan's lakes and seas aren't water. They're liquid methane and ethane, kept liquid by Titan's frigid temperatures of about -180 degrees Celsius. Titan is utterly alien. It's far too cold for water-based life as we know it, but it has extraordinarily complex organic chemistry. The atmosphere is full of complex organic molecules, including tholins, complex carbon compounds that rain down onto the surface. Some scientists speculate that Titan could host exotic life forms based on liquid methane instead of water, organisms that would breathe hydrogen instead of oxygen and metabolize acetylene instead of glucose. This is purely speculative. We have no evidence that such life exists or even that it's possible. But Titan represents a natural laboratory for studying organic chemistry in an environment radically different from Earth. Webb is studying Titan's atmosphere and surface, mapping its seasonal changes, tracking cloud formation, and analyzing the composition of its lakes and seas. These observations help us understand Titan's complex chemistry and whether it might support any form of life, however exotic. What's emerging from all of this research is a spectrum of habitability. Earth-like life, water-based, carbon-based, requiring oxygen and moderate temperatures, might be common, or it might be rare. But life itself, in forms we haven't imagined, might be far more widespread. The universe might be filled with microbial life in subsurface oceans, exotic chemistries thriving in atmospheres nothing like Earth's, organisms that would barely register as alive by our current definitions. Life might exist in clouds of Venus, in the methane lakes of Titan, in the subsurface of Mars, in the ocean of Enceladus. Or it might be rare, with Earth representing a unique confluence of factors that hasn't been replicated elsewhere. Webb won't definitively answer the question of whether we're alone. That would require visiting these worlds, collecting samples, performing detailed experiments. But it's bringing us closer than we've ever been to knowing whether life exists beyond Earth. Every spectrum it captures, every atmosphere it analyzes, every molecule it detects is a piece of the puzzle. And perhaps in the not-too-distant future, Webb will see something that makes us stop and reconsider our place in the cosmos. A combination of gases that shouldn't exist together, a chemical fingerprint that points unmistakably toward biology, a sign that somewhere out there under an alien sun, life has found a way. The search continues, and with Webb watching, we've never had a better chance of finding an answer. The detection of life beyond Earth would be the most profound discovery in human history. It would tell us that life is not unique to our world, that the processes that led to us have occurred elsewhere, that we're part of a universe where biology is a natural outcome of chemistry and physics. Or, if we search thoroughly and find nothing, that too would tell us something profound, that life might be incredibly rare, that Earth might be special, that the conditions necessary for biology might be harder to achieve than we thought. Either answer would reshape how we see ourselves and our place in the cosmos. And Webb is helping us find that answer. There's something profoundly moving about looking at the universe through Webb's eyes and realizing that you're looking at your own history. The carbon in our cells, the iron in our blood, the calcium in our bones, all of it was forged in the hearts of stars that died before our sun was born. We are, quite literally, made of stardust, connected through an unbroken chain to the Big Bang itself. Webb is helping us trace that story back to its beginnings, connecting the dots between the first stars and ourselves. When we observe the earliest galaxies with Webb, we're not just seeing distant objects, we're seeing the cosmic forges where the first heavy elements were created. In the moments after the Big Bang, the universe was impossibly hot and dense, filled with fundamental particles, quarks, electrons, photons. As it expanded and cooled, these particles combined into protons and neutrons, and then into the nuclei of the lightest elements. Big Bang nucleosynthesis, the process of element formation in the first few minutes after the Big Bang, created hydrogen, helium, and traces of lithium. That's it. 3 elements out of the roughly 90 that occur naturally. Everything else, every element heavier than helium, which astronomers collectively call metals, had to be created inside stars. The first generation of stars born from primordial gas in the universe's first 100 million years were likely massive and short-lived. These population 3 stars, which have never been directly observed but are predicted by our models, contained only hydrogen and helium. No carbon, no oxygen, no iron, nothing but the primordial elements from the Big Bang. These stars burned brilliantly for perhaps a few million years, fusing hydrogen into helium in their cores. As they exhausted their hydrogen fuel, they began fusing helium into heavier elements: carbon, oxygen, neon, magnesium. The most massive stars continued this process, building up layers like an onion, with each layer fusing a different element. Silicon fusing into iron, sulfur into various elements, the stellar core growing richer in heavy elements. But iron is special. It's the most stable element, the peak of the binding energy curve. Fusing iron into heavier elements doesn't release energy, it requires energy. So when a massive star's core becomes iron, fusion stops. The core can no longer support itself against gravity. In a fraction of a second, it collapses, then rebounds in a catastrophic supernova explosion that can briefly outshine an entire galaxy. In that explosion, and in the incredible conditions it creates, elements heavier than iron are formed: copper, zinc, silver, gold, uranium. The explosion scatters all of these newly forged elements into space, enriching the interstellar medium with the chemical ingredients for future stars and planets. The second generation of stars formed from gas enriched by these first stellar deaths. They had metals in their composition from birth, perhaps only a tiny fraction, but enough to change their properties and evolution. When these second-generation stars died, they added even more heavy elements to the cosmic mix. Generation after generation, stellar lifetimes and deaths gradually built up the periodic table. Carbon from dying stars, oxygen from supernovae, iron from stellar cores, gold and platinum from neutron star mergers. Every element with a specific stellar origin, a specific cosmic history. Webb can trace this chemical evolution by studying galaxies at different cosmic epochs. By analyzing the spectra of distant galaxies, decoding the light they emit to determine what elements they contain, astronomers can map how the universe's chemical composition changed over billions of years. What we're finding is that this process happened faster than we expected. Some early galaxies already show surprising abundances of heavy elements, suggesting vigorous star formation and efficient recycling of stellar material. The universe was quick to create the chemical building blocks necessary for rocky planets and, eventually, life. One particularly interesting observation involves detecting oxygen, carbon, and other elements in galaxies that existed less than 1 billion years after the Big Bang. These elements had to be created by early generations of stars, which means stars were forming, living, and dying in rapid succession in the early universe, enriching the gas from which new stars would form. This rapid chemical enrichment set the stage for everything that would come later, including us. But understanding our origins requires more than just chemistry. It requires understanding how those chemicals came together to form planetary systems like our own. Our solar system formed about 4.6 billion years ago from the collapse of a molecular cloud. The same process Webb now observes happening around other young stars. That primordial cloud, located somewhere in what is now the Orion arm of the Milky Way galaxy, contained the accumulated debris of countless previous stellar generations. Metals forged in stellar cores, organic molecules synthesized in the atmospheres of dying stars, dust grains formed in supernova ejecta. As this cloud collapsed under its own gravity, it began to spin, flattening into a disk through conservation of angular momentum. In the center, accumulating material heated up until nuclear fusion ignited. Our sun was born. In the disk around it, dust grains began colliding and sticking together, gradually building up the planets we know today. Webb is studying systems at every stage of this process, from the initial collapse of molecular clouds to mature planetary systems billions of years old. By comparing these observations to models of our own solar system's formation, astronomers can test their understanding of how planets form and what conditions are necessary to create a system like ours. One key question is, how common are solar systems like ours? We know that planetary systems are abundant. Most stars seem to have planets. but systems with small, rocky planets in stable, circular orbits in the habitable zone around a sun-like star might be more rare. Many observed systems have hot Jupiters, planets on eccentric orbits, or other configurations unlike our solar system's relatively orderly arrangement. Webb's observations are helping answer this by revealing the diversity of planetary architectures and the processes that create them. We're learning that our solar system's configuration, while not necessarily rare, is one outcome among many possibilities. The specific sequence of events that led to Earth being habitable, Jupiter's formation preventing Mars from growing larger, Earth's acquisition of water, the giant impact that formed the Moon, might be relatively uncommon. Or maybe it's not. Maybe habitable, Earth-like planets are common, and we just haven't detected enough of them yet to know for sure. Webb's ongoing observations will help answer this question. But beyond understanding how planetary systems form, Webb is also shedding light on the conditions of early Earth and how life might have emerged. By studying the atmospheres of rocky exoplanets, particularly young ones, astronomers can glimpse what Earth's atmosphere might have been like billions of years ago. Early Earth was very different from today. No oxygen in the atmosphere, possibly a thicker greenhouse effect from carbon dioxide and methane, intense volcanic activity constantly reshaping the surface, and bombardment by asteroids and comets delivering water and organic molecules. This period, the first billion years of Earth's history, is called the Hadean Eon, named after Hades, the Greek underworld, because scientists once thought Earth was a hellish, molten world during this time. We now know it was less extreme, with liquid, water oceans possibly existing as early as 1.3 billion years ago, just a few 100 million years after Earth formed. Webb can study planets in similar states, analyzing their atmospheric chemistry and surface conditions. What gases were present in young planetary atmospheres? How did atmospheres evolve over time as planets cooled and geological activity changed? What role did volcanic outgassing, asteroid impacts, and stellar radiation play in shaping early planetary environments? One particularly interesting area of research is the delivery of water and organic molecules to rocky planets. Earth is a wet world. 71% of its surface is covered by oceans, but it formed in the inner solar system, where temperatures were too hot for water ice to exist. So where did our water come from? The leading theory is that much of Earth's water was delivered by comets and asteroids from the outer solar system, regions cold enough for ice to exist. These icy bodies, gravitationally perturbed by the giant planets, showered the inner solar system during a period called the Late Heavy Bombardment, about 4 billion years ago. They crashed into Earth, delivering water and organic molecules along with the destructive energy of their impacts. Webb can study the composition of comets, asteroids, and the debris disks around young stars to understand how these materials are distributed and delivered to forming planets. The telescope has already made observations of comets in our own solar system, analyzing their composition and comparing it to the water and organic molecules found on Earth. These studies reveal that the building blocks of life, water, amino acids, organic molecules, are common throughout the cosmos, delivered to countless planets by the same processes that seeded Earth. Meteorites that have fallen to Earth contain amino acids, the building blocks of proteins. They contain nucleobases, components of DNA and RNA. They contain simple sugars and lipids. This means that the chemical ingredients for life don't have to be synthesized from scratch on every planet. They're delivered from space, part of the standard package that comes with planet formation. If the chemical ingredients are ubiquitous, and if they're commonly delivered to rocky planets in habitable zones, then perhaps the emergence of life is not a rare cosmic accident, but a natural outcome when the right conditions exist. This raises profound questions about life's origins on Earth. We know that life existed on Earth at least 3.5 billion years ago, possibly earlier. Fossil evidence shows microbial life from that era, and some scientists argue that chemical signatures in rocks suggest life might have existed 3.8 or even 4 billion years ago, almost as soon as Earth became habitable after the late, heavy bombardment. If life arose quickly on Earth almost as soon as conditions permitted, that suggests life might emerge readily wherever conditions are suitable. Or it might mean that life's origin was a rare fluke that happened to occur early on Earth. We can't know for certain from one example. This is why the search for life on other worlds is so important. It's not just about finding aliens, it's about understanding how common or rare the process of abiogenesis, life arising from non-life, might be. Webb is also helping us understand the role of stars in creating habitable environments. Not all stars are equally suitable for life as we know it. Massive stars, several times the mass of the Sun, burn hot and bright, but live only millions of years, potentially not giving life enough time to arise and evolve. Very small stars, red dwarfs less than half the Sun's mass, live for trillions of years, but produce intense radiation and flares that might sterilize planetary surfaces or strip away atmospheres. Sun-like stars, stable, long-lived, providing moderate radiation, might be the sweet spot for habitability. They live long enough for life to evolve, billions of years, but they don't subject nearby planets to extreme radiation environments. By studying planets around different types of stars, Webb is mapping out which stellar environments are most conducive to life. This informs our search for biosignatures and helps us understand the factors that made our solar system, orbiting a medium-sized yellow star, suitable for life. Understanding our origins is about more than satisfying curiosity. It's about placing ourselves in context, understanding how common or rare our existence might be, and contemplating whether the story that led to us, from the Big Bang to the formation of Earth to the emergence of life to the evolution of intelligence, is being replayed on countless other worlds throughout the universe. Webb is showing us that the ingredients and processes that led to us are common. Stars form throughout the universe. Planets coalesce around most of those stars. The chemistry necessary for life is present from the beginning. The delivery mechanisms that brought water and organics to Earth operate around other stars too. The specific path that led to human beings, the particular sequence of evolutionary events, the mass extinctions and radiations, the environmental changes and adaptations, might be unique. But the general story of cosmic evolution creating complexity, of chemistry giving rise to biology, appears to be written into the nature of the universe itself. In looking out at the cosmos with Webb, we're looking back at our own origins, tracing the chain of events that stretches from the first stars 13 billion years ago to this moment, right now, as you absorb these words. We are the universe's way of understanding itself, collections of atoms arranged in such a way that we can contemplate the atom's origins. And Webb is our latest, most powerful tool in that grand endeavor, connecting us to our cosmic heritage, showing us how the universe built the elements, the stars, the planets, and potentially the life that led to us. The James Webb Space Telescope represents a milestone in humanity's exploration of the cosmos, but it's also just the beginning. The discoveries Webb is making are laying the groundwork for the next generation of space exploration, inspiring new missions and new ways of thinking about how we study the universe. One of the most immediate impacts of Webb's observations is how they're shaping future mission planning. Every surprising discovery, the unexpectedly massive early galaxies, the diverse exoplanet atmospheres, the complex chemistry in stellar nurseries, is guiding scientists in designing instruments and missions that can follow up on these findings. For instance, Webb's study of exoplanet atmospheres has revealed which types of planets are most interesting and which observational techniques work best. This is directly informing the design of future missions dedicated to exoplanet characterization. The Habitable Worlds Observatory, currently in the early planning stages, is conceived as a next-generation space telescope specifically optimized for studying potentially habitable planets and searching for signs of life. Unlike Webb, which observes primarily in infrared, this future mission would focus on visible and ultraviolet light, complementing Webb's observations and providing a more complete picture of exoplanet environments. The Habitable Worlds Observatory would use a technique called coronagraphy to block out the star's light, allowing it to directly image planets orbiting nearby stars. This is extraordinarily difficult. The star is billions of times brighter than the planet, but with advanced technology, it's possible. Direct imaging would allow us to study these planets in ways that transmission spectroscopy can't, potentially even resolving features on their surfaces or detecting seasonal changes. Ground-based astronomy is also evolving in response to Webb's discoveries. Extremely large telescopes currently under construction, the 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope, with mirrors 30 to 40 meters across, will work in tandem with Webb. While Webb observes from space in infrared, these ground-based giants will provide incredibly detailed observations in visible light, studying the same objects from a different perspective. Their enormous mirrors will collect far more light than Webb, allowing them to study faint objects in exquisite detail. Together, space and ground-based observatories will create a comprehensive view of the cosmos that neither could achieve alone. But perhaps the most profound impact of Webb's observations is on our understanding of what questions we should be asking. Before Webb, we had theories about galaxy formation, star formation, and planetary atmospheres. Webb has shown us that reality is more complex than our theories predicted. This has sparked new theoretical work, new computer simulations, new laboratory experiments trying to understand the physical processes Webb is observing. Cosmologists are refining their models of early galaxy formation, trying to understand how galaxies could become so massive so quickly. Astrophysicists are studying the detailed physics of star formation, incorporating the complex chemistry Webb has revealed. Planetary scientists are developing new models of atmospheric dynamics to explain the diverse exoplanet atmospheres Webb has discovered. This cycle, observation driving theory, theory predicting new phenomena to observe, is how science advances. Webb isn't just collecting data, it's actively reshaping the scientific questions we pursue and the frameworks we use to understand the universe. Consider the search for life. Webb is showing us that rocky planets with atmospheres are common, and that those atmospheres are chemically diverse. This is guiding astrobiologists in thinking more broadly about what biosignatures might exist on worlds very different from Earth. If we find methane and oxygen together on a rocky planet orbiting a red dwarf star, do we interpret that the same way we would around a sun-like star? What if the planet has a thick atmosphere of carbon dioxide with traces of phosphine, a gas that on Earth is primarily biological? Webb's observations are forcing us to think more creatively about what life might look like and where it might exist. The technology developed for Webb is also influencing future missions. The sunshield technology that keeps Webb cold could be adapted for other infrared missions. The mirror deployment mechanism could be scaled up for even larger space telescopes. The ultra-sensitive infrared detectors could be improved and used in future instruments. Future telescopes might use even larger segmented mirrors, folding to fit in rocket fairings and then deploying in space with even greater precision than Webb achieved. Some concepts envision space telescopes with mirrors 10 or 15 meters across, significantly larger than Webb assembled in space from multiple launches. There's also growing interest in missions to the outer solar system, inspired partly by Webb's observations of icy moons. The Europa Clipper mission, launching in 2024, will conduct detailed reconnaissance of Jupiter's moon Europa, flying by the moon dozens of times and studying its ice shell, subsurface ocean, and potential for habitability. This mission builds on Webb's compositional studies of Europa's surface. Future missions might visit Enceladus, flying through its plumes to sample the subsurface ocean directly. A mission to Titan might include a lander or even a submarine to explore its methane lakes. These ambitious concepts are motivated by the desire to search for life in our own solar system, informed by Webb's observations showing that these worlds have complex chemistry and potentially habitable environments. Beyond our solar system, some scientists are even dreaming of interstellar probes. Projects like Breakthrough Starshot envision tiny spacecraft accelerated by powerful lasers to a significant fraction of light speed, capable of reaching the nearest stars within a few decades rather than millennia. These missions are still highly speculative, facing enormous technical challenges. But they're motivated by the same drive that created Webb: the desire to see directly, to visit, to explore. Webb is showing us tantalizing targets, planets that might be habitable, systems with unusual characteristics that make the case for eventual interstellar exploration. Imagine a tiny spacecraft weighing just a few grams, accelerating to 20% of light speed and reaching Proxima Centauri in about 20 years. It could fly past Proxima Centauri b, the closest known exoplanet, taking high-resolution images and measurements before continuing into interstellar space. The data would take another 4 years to reach Earth, but we would finally have close-up observations of a planet around another star. This isn't science fiction, it's serious engineering being explored by researchers today. The challenges are immense, but they're not necessarily insurmountable. But let's think even further ahead. What comes after Webb and its immediate successors? Some scientists envision space-based interferometers, multiple telescopes flying in formation, working together to create images with resolution far exceeding what any single telescope could achieve. By combining the light from several telescopes separated by hundreds or thousands of meters, these interferometers could achieve the resolution of a telescope as large as the separation between the individual units. Such an interferometer could directly image Earth-sized planets around nearby stars with enough resolution to see continents and oceans, to detect seasonal changes in vegetation, possibly even to see cities on the night side, if they exist. We could study exoplanets not as single pixels, but as actual worlds with geography, weather, and potentially ecosystems. Other proposals involve telescopes positioned even farther from Earth, perhaps using the Sun itself as a gravitational lens. Einstein's general relativity predicts that massive objects bend light, and the Sun's gravity can focus light from distant objects. At about 550 astronomical units from the Sun, roughly 14 times farther than Voyager 1 has traveled, the gravitational focusing effect becomes strong enough to use. A spacecraft positioned at this distance could theoretically use the Sun as a natural telescope, achieving resolution fine enough to image surface features on exoplanets dozens of light-years away. The technical challenges are staggering. Getting a spacecraft that far, keeping it precisely positioned, dealing with the Sun's corona and solar wind. But the potential payoff is extraordinary. These ideas sound like science fiction, but so did Webb until we built it. Every technological challenge that seemed insurmountable, the deployment sequence, the mirror, alignment, the cryogenic cooling, was solved through ingenuity and persistence. There's no fundamental reason future challenges can't be overcome similarly. Webb is also changing how we think about collaboration in space science. This is an international project with contributions from NASA, the European Space Agency, and the Canadian Space Agency. Scientists from around the world compete for observing time through a peer review process, and they collaborate on analyzing the data. This model of international cooperation might become the standard for future flagship missions. The cost and complexity of cutting-edge space telescopes are so great that no single nation can easily afford them. But by pooling resources and expertise, humanity can tackle questions that would be impossible for any one country to address alone. There's something inspiring about that vision. Humanity united not by borders or politics, but by shared curiosity about the cosmos. Webb represents that ideal in action, and its successors will likely continue that tradition. In a sense, the future of space exploration is already happening. Every observation Webb makes informs the next generation of missions. Every discovery raises new questions that will drive decades of research. The images Webb captures today inspire the next generation of scientists and engineers, children who see the pillars of creation or the deep field images and decide they want to understand the universe. We stand at a unique moment in history. We're the first generation with the technology to seriously search for life beyond Earth, to study the formation of the first galaxies, to watch planets being born around distant stars. Previous generations could only wonder about these things. Future generations will take them for granted, growing up in a world where we know whether life exists elsewhere. Where we understand how the first galaxies formed, where exoplanet atmospheres are catalogued and studied routinely. But we're living through the moment of discovery, experiencing these revelations for the first time. We get to feel the shock and wonder of seeing things no human has ever seen before, learning things no one has ever known. Webb is our guide on that journey, and while it won't last forever, its fuel for maintaining its orbit is finite. Its instruments will eventually degrade. The knowledge it's providing will endure, forming the foundation for centuries of future exploration. The spacecraft has enough fuel to operate for at least 20 years, possibly longer. That's 2 decades of observations, discoveries, and revelations. Think about what we've learned in just the first 2 years of operations. Now imagine what we'll know after 20 years of Webb observations. The universe is vast, ancient, and strange, but it's also knowable. With instruments like Webb, with human curiosity and ingenuity, we're slowly peeling back the layers of cosmic mystery, one observation at a time. The journey is far from over. In fact, it's only just beginning. We've traveled far in this exploration, from the technical marvel of Webb's construction to the profound questions it's helping us answer about galaxies, stars, planets, and the search for life. But now, as we reach the end of this journey, it's worth pausing to reflect on what Webb truly represents and what its discoveries mean for us. The universe that Webb is revealing is not the universe we expected. We thought we understood how galaxies formed, but Webb showed us massive, mature galaxies existing impossibly early in cosmic history. We thought we knew the timeline of black hole growth, but Webb found supermassive black holes that grew far faster than our theories predicted. We thought planetary atmospheres would fit neatly into our models, but Webb discovered chemical diversity that challenges our assumptions at every turn. At every turn, the universe has proven stranger and more complex than our theories suggested. But this isn't a failure of science. It's precisely how science is supposed to work. We build models based on the best available data, then we test those models against new observations. When reality doesn't match our expectations, we don't ignore the data or declare defeat. We update our models, refine our theories, develop new frameworks, and try again. This is how knowledge grows, how understanding deepens. Webb is giving us the gift of confusion, forcing us to confront how much we still don't understand. And there's something beautiful about that, about recognizing the limits of our knowledge and pushing against them, about being humble enough to admit when we're wrong and curious enough to keep searching for better answers. Consider the audacity of what we're attempting. We're trying to understand a universe that's 13.8 billion years old and approximately 93 billion light-years across in its observable portion. We're trying to comprehend a cosmos containing an estimated 2 trillion galaxies, each with hundreds of billions of stars. We're trying to understand the first moments after creation, the nature of dark matter and dark energy, the potential for life on worlds we'll never visit, the ultimate fate of everything that exists. It's an audacious goal, perhaps even an impossible one in its totality. But that's never stopped us before. Throughout history, humans have looked up at the sky and wondered. We've told stories about the stars, navigated by them, worshipped them, feared them, studied them. We've gone from thinking Earth was the center of everything to understanding that we orbit an ordinary star in an ordinary galaxy in an ordinary region of a vast universe. That might seem like a demotion, a cosmic humbling. Each successive discovery pushed us further from the center. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. There is no center. We're just here on a small planet, orbiting an average star in the suburbs of a typical spiral galaxy. But there's another way to look at it. We are ordinary star stuff that has become self-aware. We are matter that has organized itself in such a way that it can contemplate its own origins, that builds telescopes and writes equations, that wonders about its place in the grand cosmic story. We are the universe experiencing itself, understanding itself, marveling at itself. And that's extraordinary. Carl Sagan famously said, "We are a way for the cosmos to know itself." The atoms that make up your body, the carbon, oxygen, nitrogen, iron, were forged in stellar furnaces billions of years ago. They've been part of stars, part of interstellar gas clouds, part of the disk from which our solar system formed, part of the early Earth, part of ancient organisms, and now part of you. You are literally made of recycled star material, atoms that have been on an extraordinary journey through space and time. And now, those atoms are arranged in such a way that they can think about where they came from, can build instruments to study the universe, can feel awe and wonder at cosmic beauty. Webb is the latest expression of that drive to understand. It represents thousands of people working for decades, solving problems that seemed unsolvable, creating an instrument of almost absurd precision and capability. It represents nearly $10 billion invested not in immediate practical returns, but in pure knowledge, in satisfying curiosity about the cosmos. Some might question whether that investment was justified. After all, Webb's discoveries won't cure cancer, or solve climate change, or end poverty, or feed the hungry. Why spend so much effort and resources studying distant galaxies when we have pressing problems here on Earth? But this misses something fundamental about what makes us human. We are a species that asks questions, that seeks to understand, that creates art and explores ideas not because they're immediately useful, but because they're meaningful. The same impulse that drives us to create music and literature and philosophy drives us to build telescopes and explore the cosmos. And sometimes, knowledge pursued for its own sake does yield practical benefits. The technology developed for space missions has found applications in medicine, communications, materials science, and countless other fields. GPS, satellite communications, weather forecasting, medical imaging, all owe debts to space technology. The inspiration provided by cosmic discovery sparks young minds to pursue science and engineering careers, leading to innovations we can't predict. But even if Webb's only contribution were to expand human knowledge and inspire wonder, that would be enough. There's inherent value in understanding our universe, in knowing our cosmic context, in grasping how we came to be. There's value in the beauty of Webb's images, in the profound questions they raise, in the sense of connection they create between us and the vast cosmos. And there's practical wisdom too. Seeing Earth from the cosmic perspective, a pale blue dot as Voyager 1 showed us, or a tiny marble in Webb's deep fields, reminds us how precious and fragile our world is. It gives us perspective on our squabbles and divisions, reminding us that we're all aboard the same small planet, the only home we've ever known, traveling through an incomprehensibly vast universe. That perspective can inspire us to take better care of our world, to resolve our conflicts, to work together toward common goals. If we can cooperate to build something as extraordinary as Webb, what else might we accomplish together? There's something profound about living in a time when these discoveries are happening. Future generations will grow up knowing that the early universe was strange and complex, that exoplanets have diverse atmospheres, that planets form around most stars. These facts will seem obvious to them, incorporated into their basic understanding of the cosmos from childhood. But we're experiencing these discoveries for the first time. We're the generation that gets to feel the shock and delight of seeing Webb's first images, the confusion of finding galaxies that shouldn't exist, the excitement of detecting molecules in alien atmospheres. We're living through a golden age of cosmic discovery, witnessing revelations that will be remembered for centuries. And Webb's mission is far from over. The telescope is expected to operate for at least another decade, possibly two. Each year will bring new observations, new discoveries, new mysteries to solve. The story we've told here is just the beginning of Webb's legacy. Somewhere in Webb's future observations might be the detection of a biosignature in an exoplanet's atmosphere. The first strong evidence that life exists beyond Earth. Or the identification of population 3 stars, those first stars predicted by theory, but never observed. Or the solution to the mystery of dark matter, revealed through precise gravitational lensing measurements. Or discoveries we can't even anticipate yet, phenomena we didn't know to look for. That's the nature of exploration. You don't always find what you're looking for. Sometimes you find something better, something unexpected, something that opens entire new fields of inquiry. As we close, think about this. The light that Webb collected to create its images traveled for billions of years to reach us. Photons emitted by stars in the early universe, by galaxies forming when the cosmos was young, by distant quasars powered by supermassive black holes. All of that light journeyed through space for eons, traveling at the ultimate speed limit, crossing unimaginable distances. And then, at just the right moment, those photons encountered our telescope. They struck Webb's gold-coated mirror, were focused onto its detectors, were converted to electrical signals, transmitted to Earth, processed by computers, and transformed into images that human eyes could see and human minds could contemplate. There's profound poetry in that, a conversation across cosmic time and space, a connection between the ancient universe and the present moment, between distant galaxies and the instrument we built to observe them. We are small, our lives are brief. Our planet is a speck in an incomprehensibly vast cosmos. But we are also magnificent, capable of building instruments that can see to the edge of the observable universe, capable of understanding physics and chemistry and mathematics well enough to decode what we observe, capable of asking deep questions about existence and meaning, and our place in the grand scheme of things. The James Webb Space Telescope is a testament to human ambition, ingenuity, and curiosity. It's a machine, yes, metal and glass and electronics, but it's also a monument to our desire to understand, to explore, to push beyond what we know, into the unknown. And what it's revealing, a universe more complex, more mysterious, and more wondrous than we imagined, reminds us that no matter how much we learn, there's always more to discover. The cosmos continues to surprise us, challenge us, and inspire us. The story of the universe is also our story. We are made of atoms forged in stellar cores, organized by the same physical laws that govern galaxies and black holes, part of the same cosmic evolution that stretches from the Big Bang to this present moment and beyond into the future. Webb is helping us read that story, chapter by chapter, revelation by revelation. And in doing so, it's helping us understand not just the universe out there, but our own origins, our own nature, our own place in the cosmic tapestry. So the next time you look up at the night sky, remember, those stars you see are not just distant lights. They're other suns, perhaps with their own planets, their own stories. The light you see left those stars years, decades, or centuries ago. You're literally seeing the past. And remember too that we're not just passive observers of this cosmic drama. Through instruments like Webb, through human curiosity and ingenuity, we're active participants. We're asking questions, seeking answers, slowly assembling a picture of how the universe works and how we came to be part of it. The universe is vast, ancient, beautiful, and strange. It operates according to physical laws we can understand through observation and mathematics. It's filled with wonders we're only beginning to discover: black holes and dark matter, exoplanets and stellar nurseries, the first galaxies, and the possibility of life beyond Earth. And somewhere in all of that vastness, on a small rocky planet orbiting a medium-sized yellow star, a species has emerged that can build telescopes, decode the light from distant galaxies, and contemplate the nature of existence itself. That's us. We are the universe made conscious, made curious, made capable of wonder. Webb is our window into cosmic mystery, our tool for exploration, our means of understanding. And through it, we're learning that the universe is far stranger, far more magnificent, and far more knowable than we ever dared imagine. The journey of discovery continues. The questions multiply even as we find answers. The cosmos keeps revealing new layers of complexity and beauty. Keep looking up. Keep asking questions. Keep wondering. Because somewhere out there, in the light of distant stars, in the atmospheres of alien worlds, in the hearts of forming galaxies, answers are waiting to be found. The universe is speaking to us. And with Webb, we're finally learning to listen. This has been Infinite Science. Thank you for joining us on this journey through the cosmos as revealed by the James Webb Space Telescope. Until next time, clear skies and endless wonder.